And I'll say, welcome back, everybody, to PCB Design Fundamentals Part 2. This is week 4. Today, we're going to be talking about manufacturing and some of the challenges we face there. But before we get started, I know, Fazil, I saw you had your hand up earlier. Did you have a question? And are you able to hear me out there now?
Yes, I can hear you.
Okay, excellent. And I saw your hand up, so did you have a question out there?
Yes, I have a question.
Sure.
So I have noticed something in Altium when I worked in the last assignment. When I
Okay.
connect a pad from the top layer to
Mm-hmm.
the bottom layer, it automatically insert a through-hole via from layer 1 to layer 10. But when I do the opposite, connecting a pad from the bottom to the top, it insert a micro via with
Yeah, the micro stacked on the buried, stacked on another micro via. Yeah, I have not
So
figured
what
out.
is the difference?
It's Altium's programming. For a while there, it was doing that always if you had those available. Hmm. It won't hurt anything. For this design, it won't hurt anything. Since we're going to end up using micro vias to escape out of the BGA, so we predefined that that was a valid structure. It's something under the hood of Altium of how it's trying to decide that. There is ways to go in after the fact and change that to say, no, I really want a full through via here, but it's not, for the purpose of this class, it's not going to hurt anything to have it micro on buried versus a full through. It's just something in how Altium's program under the hood decides based off of the order of layers that you go through, right, of whether or not you do a stacked with a buried. Basically, what Altium's tool is trying to do is to use the smallest via stack it can. So, for example, if we go back to, we'll reopen Surrenders here. We'll go reopen their board. Now that I didn't mess it up with the little demo I was doing there. So, as it's thinking about opening back up, back in the original state it was in before I was messing with it. For example, let's take this one right here. And let's route this one only down to layer 2. Right, so I'll take this one right here, I'll pause right here, and I'll only go to layer 2. It's going to give me the micro via right there. Now, not going to choose the size, but it's going to give me the micro via because it says I don't need via to go any further because I'm only going from layer 1 to 2. But if I were to route the same trace right over here and say want to go all the way down to layer 10, here in this case on mine, it did exactly what we thought, which is it created a 3 stack, right? So it said there's actually 3 vias there. There's a 1 to 2, a 2 to 9, and a 9 to 10 going that way. So it basically said that's what it came up with for its easiest way. Sometimes it figures that its only way it can do it is with a full through via, but for the most part, it tries to use the stacked and the micros and stacks them to try and get to the smallest vertical z-axis dimension. So if you only need to go from 1 to 2 and you have a via that's defined from 1 to 2, it goes directly to from layer 1 to 2. Okay. Does that make sense to you?
Yes, but when I'm designing a practical board, not in our application, are there any concerns should I take when I do this stacks?
There are a few. It's preferred to do a staggered versus a stacked if you're going to do micro via on vias like that. There's a little bit of concern in processing cost. And like I said, there is ways to go back around and fix this after the fact. And there are ways to write complex rules. For example, we really only need the micro vias like this in the uh, in the area where the BGA is. So we could write a rule that says you can only use the microvias in uh, in the one area, right? Otherwise, the only V you're allowed to use is the full through. So there's ways to write rules to restrict where the microvias can be used at, and so on. But yes, there will be a few concerns whenever I do a microvia, stacked microvias. The via below has to be filled and then capped and planarized with copper so that there's a surface for the microvia to connect to. So there is a little bit of extra manufacturing challenge doing this, the stack style here. So usually we just go back after the fact and clean it up, or we can write a rule uh, that says using these rooms, using an area says, okay, here's a via style that is only allowed to be used uh, in this area right here. Otherwise, you can only use the full through vias and so on. But great question, Fazil.
Okay, thank you.
Okay. Let me close that down again because again, I don't want to save any changes. Close. There's close. Don't save changes. All right. Great questions. While that's closing, let me go ahead and pull up the slides for today. So as we said, today we're going to talk manufacturing and go that way. Okay. Those coming back from PCB1, these first slides will be a refresher. We went over this in week 1 of PCB1. For everybody else, this will be some new material here. Okay. So the first thing we're going to talk about is just the basic fabrication process. We're going to look at a simple little 6-layer board here. How would we go about fabricating a 6-layer board using standard full through via technology or full plated through hole technology, surface mount pad here, and 6 layers of construction here. So a typical 6-layer construction is what we're going to call, or what the fabricators like to call, foil construction. This is going to be the most common method of fabricating our printed circuit boards here, and this is where we use our foil layers as our sheets of foil as our 2 outermost layer, and those cores that we talked about last week will be layers 2, 3, and then 4, 5 right here. In this construction right here, our outermost layer is foil. Then we have prepreg, 1 or more prepreg sheets between layers 1 and 2. The layers 2, 3 are one of those cores that we talked about last week. More prepreg, another core, more prepreg, and another sheet of foil. Now we'll notice here, and I should put this down, okay, foil construction, and we'll say it like this, number of cores is equal to number of layers divided by 2 minus 1. Okay, so the number of cores that you need to process before you laminate in foil construction is going to be the total number of layers divided by 2 minus 1. So with 6 layers, divide by 2 is 3, subtract 1 is 2, so we have to process 2 cores. Okay. On the other hand, if we have cap construction, which is what we call it, where we reverse the process, right? Where if I make the layer 1 to 2 a core, then prepreg would be between layers 2 and 3. A core would be layers 3 to 4. Prepreg would be layer 4 to 5, and another core would be layer 5 to 6. So if we reverse that, where the outermost layers are on cores, We are going to call that cap construction, and the total number of cores that you have to process is number of layers divided by 2. So you'll notice it is more expensive and more time consuming to do the cap construction, where the outer layers are defined as cores instead of foils, because you have to process 3 individual cores before you can laminate. So I have one less processing step with the foil construction. We're also going to see here in a minute why this is going to be preferred. Okay. Now, inner layer processing. Each of those inner layer cores needs to be processed individually, and after all inner layer cores are processed, the layers are stacked together for lamination. We can think of a core, and I've mentioned this before, we can think of one of our cores as simply a very thin 2-layer printed circuit board, where we've got laminate material here that's fully cured and fully hardened. We've got solid copper sheets here and here. It looks something like this. The way we're going to go about processing in the classic method, most high-end fabricators nowadays do what it's going to be called laser direct imaging, but we're going to talk about this. I will put that here. Newer method is it's called LDI. New method, LDI. For the photo tool. Okay, so historically what we do is we take our core, we apply a sheet of material called a photoresist or etch resist. It's typically a chemical film. It's like a tacky sheet of not quite as strong as an adhesive, but it's like a kind of tacky sheet of material. It's applied to the layer. And then we have what we call a photo tool or a film. Typically, it's a sheet of mylar film that's been impregnated with either silver emulsion or old diazo ink. And that ink is photosensitive. It goes through a standard uh, photographic process, photographic imaging process, where the area we wish to remove copper is turned a dark color. That makes the photo tool a negative, which says that the area that does not have the immersion in it will then be exposed to UV light, which will harden and cure the photoresist chemical to the surface of the board in the area we wish to keep the circuit, which means it's a positive image of our circuit itself, then making the film the negative image. Okay. So again, this is how we're going to do this. Now, with this new method, the LDI, rather than having a single UV light source up here that exposes all the material at once, you have a movable laser head that uses UV laser light instead of direct UV fluorescent light or whatever it is up here. And that, in turn, will effectively draw the same thing. It's still the same process that you're still using UV light to cure or harden the photoresist chemical where we wish to keep the copper on our board. It's just, do we have a sheet of mylar film with the image of our circuit with light shining through it like a traditional photolithography process? Or do we directly image right onto the blue material without the need for the photo tool? All right. Now, once you have gone through the UV curing process of the blue photoresist material, you go through a washing process which will remove the uncured photoresist in the areas where you wish to remove the copper. So we'll remove the uncured film, and now we're left with something that looks like this. We've got our solid copper right here. We have our geometry here. Note, by the way, this is this cutaway view that we looked at here. This is why we only see half a circle, because we're looking cutaway view right here rather than looking at the whole thing. So we want to be able to look through and see the drilling process happening here. Okay. So that's why we see this here. So we see the trace coming in here. We see where the hole is going to be here, etc. Okay. Now, once we get to that point there, board will, or the layer will go through, the core will go through the etching process where we use a liquid chemical acid etchant chemical, which will then strip or remove the copper off of the surface, leaving us only the protected traces right here. We're going to talk in a little bit here about a phenomenon called undercut, which is going to cause us some non-ideal geometries right here, and this is called a subtractive. This is what we call a subtractive process because we start with solid copper and then we remove or subtract copper we don't want, versus an additive process where we start with base material and we deposit copper only where we want to have it. We get into that when we do RF and other specialty designs, but for the most part, traditional fabrication is going to do what we call a subtractive process where we start with solid copper, remove copper we don't want. Okay. Once we have etched the layer, we then remove the remaining film. Again, a chemical solvent and chemical and scrubbing and washing process to remove the etch resist, leaving us with the exposed copper here. You'll notice we have not drilled any holes in anything yet. We have only so far etched the XY geometry on the two layers. We will then go through an AOI inspection, more on AOI later, but AOI is automated optical inspection, where we'll check for defects, opens, shorts, over etching, under etching, and so on, deformations. So we'll do an automated optical inspection on this, and the layer pair is complete. So this, we call this a layer pair because it's a core. We have two layers right here. All the remaining inner layer pairs, right here, core, are processed the same way, and then we'll stack them together. We'll get to the lamination in a minute here, but first I want to talk about this phenomenon here called undercut. So we're going to look at, say, the formation of one trace right here, or really we're going to look at the boundary between the two traces right here. So in the ideal world, we'll have that blue photoresist chemical right here. We'll have our solid sheet of copper and our laminate material. In the ideal world, we would have these nice vertical sidewalls here. However, because we're using a liquid acid etching process right here, what we're going to find is that as the acid is eating through the vertical thickness of the copper, it will start to attack the sidewall of the copper underneath right here, and we'll end up with this non-ideal kind of concave fillet shape right here. We'll represent it as a trapezoid. We'll see that here momentarily, and we'll look at that right here. So at some time t0, again, I'm playing around with scale here just to demonstrate the purpose. I'm not saying in this case that we're thinner blue or thicker blue, thinner or thicker copper here. I'm just playing around with scale in these images just so that we can get through, go through the discussion here. So at some time t0, we will apply the acid. Technically, we submerge this in acid or have acid sprayed on it, so it's basically got liquid acid everywhere. But we'll go at time t0 here. The acid will begin to remove copper, so the acid is starting to eat down through the thickness. As it starts to eat down through the thickness, it will also start to attack the sidewall right here. It will continue until it gets through the entire thickness right here. And at some point, we will have completely etched all the way down here. And we will be left with this, what we represent as a trapezoid. It's really got more of this concavity right here. It has to do with, dynamic fluids, fluid dynamics, surface tension of a liquid, the fact that it can't get up underneath this overhang here very well. So we get this kind of concave shape, etc. But we'll have the final trace geometry right here. Note that the thicker the starting copper, i.e. the longer the acid has to eat through the z-axis thickness here, the more time it has to attack the sidewall, and therefore the more severe the undercut. Okay. Typically, it's about 1 mil per mil. It's about a 1-to-1 ratio of total undercut this way to this distance right here. And we're going to call this an etch factor, and we'll talk about that here a little bit more in a moment here. And the fabricators are going to apply what they call an etch compensation to mitigate this. Meaning what the fabricators are going to do is they are going to increase your geometry sizes. So this is one of the key things that the fabricators do with your data when they first receive your data. For example, if you put a 5 mil trace width on your board, knowing that you have, say, 1 mil thick, because we're doing 1 ounce copper, and they need to etch through 1 ounce of copper thickness here, they may increase the trace from 5 mils to 6 mils, so that after this undercutting phenomenon happens, that the final trace width, the average trace width, ends up back at the 5 mils you specified. Also note that the fabricators never measure the trace width right here at the top, nor all the way down here at the bottom. Instead, their target is to measure between 1/3 and 2/3 of the thickness. So they're trying to get an average trace width somewhere about in here. Okay. Again, your fabricator knows their process better. They should always be contacted, but this is something that every fabricator in the world does without exception, unless you explicitly put into your master drawing that they are not allowed to do etch compensation, that they have to etch with the width as you provided. Just know that if you do that, and you are expecting the 5 mils you put in there to be what you receive, that's not what you'll receive, because this is just the physics of fluids dynamics right here. Okay, once all the etching is completed, the layers will then be stacked together right here with the sheets of prepreg between the foil and the first core, sheets of prepreg between the first core and the second core, and sheets of prepreg here. Again, this is a simplified view without showing the traces here. You'd have to imagine in this ISO view that the inner cores right here do have the etching completed here, and we're going to have solid copper foil on the outer layers. Again, this is the standard process or the preferred process by the fabricators. If you do require the use of the if you do require the use of the outer cores, that's fine. The outer foil, the outermost core, copper layer will still be left solid, and they will only etch the inner layer. This is one of the other reasons fabricators do not like the cap construction method, because those two outer layers will actually see etching twice. First, they will have to protect the outer surface when they etch the underside so they can laminate, and then they'll have to come back and etch a second time. So that material there will actually see the etchant twice, more risk of contaminants and other structures being absorbed into the material. Okay. Once all the stacking is completed, the board will be put into a laminate where pressure and temperature are applied to the stack. The temperature is what raises above the glass transition temperature we've talked about, and the pressure forces the resin to flow, squeeze, and flow around all of the copper features to make sure we have a good homogeneous seal around everything. Once the board is cooled, all the layers are now fully cured, so it's now a uniform homogeneous structure in here where the prepreg layers have turned into effectively cores themselves. They're fully cured now. Once we have completed the lamination process, we go through the drilling process. This is where we're going to drill through the board to form our vias or other plated through hole structures here. Note that when I first drill through, I do not actually have an electrical connection through any of the layers. I simply have exposed conductive material of copper at this surface. Whatever, say, two inner layers I want to connect, say maybe these two right here, and maybe the bottom surface right here. Maybe this is a ground plane, return plane, whatever. So we'll see that. Again, right now I have no conductive path. I only have a hole exposing the barrel wall right here. At the barrel wall, I've exposed this copper here and here, as well as the two outer layers. Next, we're going to go and do what's called an electrolysis copper process. This process is going to use a standard chemistry process of a saturated or supersaturated solution, where copper ions are held in solution, the board is submerged, and then through a combination of control of temperature as well as vibration, we will then get a very thin skin of copper on all of our surfaces right here, both the vertical barrel wall surface as well as the two outermost surfaces. This thickness ends up being between about 20 to 100 micro inches. I don't know exactly what that is in metric. I'd have to do the conversion, but it tends to be between about 20 to 100 micro inches typically. Note also, I colored it pink here just for contrast so that when we see all the layers together in the next slide, we can see the layer delineations here. This is copper. It is the exact same copper as we have of our surfaces here. I was just concerned if I do orange with orange with orange, we're going to lose the distinction between the layers there. So I made the electrolysis pink just for contrast here in the graphic. It does not actually appear pink when we cross-section look at our boards. So, however, what this does do for us, although it cannot handle any appreciable amount of current, 20 microinches, we're talking microamps, maybe milliamps of current at most that this could handle. So this is not yet sufficient for the current handling of our board design, but what it does do now is electrically connect the top surface, the bottom surface, and whatever copper is exposed here that we want to make this connection to. Next, we're going to go through a two-step process on the outer layers before we get to the plating. So the first thing we're going to do here is we're going to go back through applying the photoresist here, but this time, however, we're going to make a negative image. So on the piece of film, if we're still using the Mylar film method, the image we're going to show is the actual trace, meaning the area that is going to get hardened on the blue etch resist where we wish to protect is actually going to be the area we wish to remove copper. So we'll put the blue etch resist in this case where we want to remove copper, not where we want to keep it, which is why we're going to call this a negative layer. The blue is the negative or where we wish to remove copper. Seems a little silly, I know. We'll get to that here in a moment. Next, now this is the point where we're going to do the additional copper plate up. This is where we're going to go through a traditional electroplating process. And this is going to give us the full thickness of copper, pretty much the same thickness as our layer here, unless we're doing a heavy copper. So this is like the class 3, the 1 mil thick of copper, etc. right here that we would have. And this is where we've got not only the original base copper on the layer, we have the thin electrolysis, but now we have the thickness of copper in our barrel wall plus the additional thickness on the surface. Okay. Once we have the plate up process here that gives us both our PTH for our barrel as well as on our surface traces right here. Next, we're going to come back and we're going to use another plating process. This is going to be what will act as our etch resist. It turns out that pure tin, as much as we don't like it because of tin whisker and other phenomenon like that, pure tin does, however, act as an excellent resist against the etchant solvent acid that attacks copper. The acid that attacks copper does not attack tin, hardly at all. So we'll put a tin plating on that surface to start with. We will then come back, remove the photoresist through its solvent-based removal, solvent and cleaning based. So remove the film. We will then go back through the same acid etching process again here. The acid etching process, maybe. The acid etching process here will then remove the copper on the surface where we don't want to keep the copper. We will then come back, leaving us only the traces left. We'll then come back and go through a chemical tin stripping process. So there are chemistries that can actually strip the tin off that surface, leaving us only the traces left. I get asked the question all the time, why did I go through this process? Why did I go through the more complicated process on the outer layer? And it goes back to this step right here, going back to what we just talked about a few slides ago with that undercutting. If I do not do this process right here, where I start and do the etch resist right here, if instead I plate the entire board with the electroplating process to get the copper thickness in the barrel wall, that means I also have that extra copper thickness where I wish to remove copper. That means if I allow this much thickness, that means my acid etching process that's going to do my copper etching will have to eat through 2 thicknesses, not 1 thickness of the copper right here, because I'd have the base foil here, plus however much thick my electroplating process was right here. And as we said previously, the thicker the copper you have to etch through, the more severe the undercut. And the more severe the undercut, both is going to take longer, and you'll have more etch compensation that'll be needed. So by doing this 2-step process with the tin and so on, we can then only need to etch through 1 copper thickness instead of 2 copper thickness, because the first copper thickness is technically an additive process of the electroplating. Okay.
And why they don't start with the top and bottom layer without copper?
Because you need the base copper for the electroplating process to work.
But you add the pink layer.
Right, but the pink layer is easier bonding to existing copper than to the surfaces. Yes, it can be done, but it is both from a uniform copper geometry thickness, which we want for signal integrity, as well as for ease of manufacturing, starting with the foil here. And I was going to put a note here, the electroplating. And I'll put a note on the slide back here for the electroless. The other problem with electroless, it can be done. It is a very, very slow process, right? So for efficiencies of time and getting your product through to you in a timely manner, it's easier and better for the fabricator to start with a foil and go through these 2 processes. So electroplating is a very fast process, but it requires the base copper so you can put an electrical current through it. It's a very low current, but a voltage, so it has a charge, so you can go through the electroplating process. However, it needs that base copper to start with. Now, the electroless, there are shops that, if you ask them for, will do fully electroless, but it's going to take a lot longer to process the board than it will to go through the standard process here. Does that hopefully answer your question?
Yes, thank you.
Okay, excellent. Okay. So again, we're going to go through all these processes here. We'll remove the tin where only our traces are left on our board now. Okay, now we have an electrically finished board. At this point, oh, there's another question out there. There's a hand up. Yes, Mattia.
So this process actually then will increase the thickness of the copper on the top and bottom layers, right? So if we start off with one oat set, so how much more, let's say, can we expect from this here process?
Hold that thought. We're getting to that.
Okay.
But I will show you that here. We'll actually do that here real quick. That reminds me, I should have had this document open. So let me open that up here. Maybe it'll open up. And actually, I am going to close my Altium down because it is a bit of a memory hog while I'm waiting on this stuff to open up. So right here in our IPC 6012, we call these performance and qualification standards or qualification performance specifications. We really mean manufacturing. So this whole 6010 series, so 6011, 6012, 6013, and so on, these are what the fabricator is required to comply with when they fabricate your board. Whoop, wrong one. I'm going to pull this one up. And in here, okay, let me get back over here. Okay, so whoop. So when it comes to the inner layers, if you remember, I mentioned last week that copper thickness, that, you know, the 4101 says that the 1 ounce copper foil is 1.35 mils thick, and I said you're never going to get that. So we'll look at the 1 ounce here. So first, we're going to say here was the nominal 34.3 microns. That's our 1.35 mils. Remember, the fabricator of the copper itself, the fabricator of the laminate itself, the isolas and so on, they're allowed a tolerance in part production, just like resistors have tolerances, right? You order a 1K ohm resistor, not every 1K ohm resistor measures exactly 1.00 K ohms, right? You have a tolerance. The same thing. I order a sheet of 1 ounce copper foil. Do I get exactly 34.30 microns? No. So the fabrication allowance for the actual 1 ounce copper, or for all the coppers actually, is plus or minus 10%. So my 1 ounce copper foil could start as thin as 30.9 microns, which is 1.2 mils thick. Then the maximum variable processing allowance. This is how much, with all those apply a chemical, clean a chemical off, apply something, clean it. That's all washing and scrubbing over and over and over again. So how much is the fabricator allowed to reduce the copper thickness further? And that says right here for 1 ounce copper, they're allowed 6 microns. So that basically says my 34.3 micron after allowed possible minimum copper thickness plus processing allowance is going to finish at about 24.9 or about 1 mil thickness. That's for inner layer without plating. Now for outer layers where we have the plating thickness, we have this chart, the external conductor thickness after plating. This is really conductors after plating. So whether it's internal or external, it should just say conductor thickness after plating. Same thing, 1 ounce. So again, we're going to start with that absolute minimum of 30.90. Now, depending on your board class, if you're class 1 or class 2, the fabricators allowed a minimum of 50.9 microns of copper addition for the plating. For class 3, it's 55. I'm sorry. They're allowed 20 microns or 25 microns added to the initial. So we'd end up at 50.9 or 55.9. So we go to 2.0 or 2.2. But now, because of the additive plating process, they're only allowed a 3 micron reduction for all the cleaning and processing steps they have to go through. So when you add, and let's just take a class 3 board, for example, if I add 25 microns, but subtract 3 microns, that's I'm adding 22 microns to my 30.9, which gives me 52.9 right here, which says I finish my 1 ounce base copper foil on my outer layer. I'm going to expect it to be approximately 2.1 mils of thickness, which if we look back up here, 2.1 mils, that's darn close to what 2 ounce copper inner foil is after processing, right? So we're basically looking at these charts right here in the 6012 based off of your board class 1 or 2 versus class 3, and whether it's with or without the plating. And these charts here will tell you what kind of numbers you can expect, both on your inner layers after all those processing steps, as well as your outer layers processing steps plus the plating step for what you can actually expect in your board when all is said and done. Does that answer your question, Mattia?
Yeah, it answers my question, but that means that actually, I mean, for the external conductor, that we have what, over 50% of increase in the copper thickness. I'm just wondering, is it then, let's say, it really meaningful to design the boards with control impedance, if that also is, let's say, it dependent on the copper thickness, if in the end what actually comes out from manufacturing will not have the copper thickness you were doing the calculations with. So I'm just wondering, how does this then, let's say, it work out in the practice?
So, two ways that works out. Number one, if you recall, I have on multiple occasions now made the comment, your fabricator is your friend. Check with them early and often. This is one of the reasons why I said when I'm routing professionally, I don't lay a single trace on any of my boards until I've double checked with my fabricator, because they know based off of their specific process how close, when they're plating their process variants, right? Are they taking the full 3 microns here, or are they only doing 2 microns of reduction, etc.? So number one, I always check with my fabricator, but number two, knowing these charts right here, these are the numbers I actually put into my stack up. And I don't remember if I did it with this class or one of my other classes, but I often show that when I'm building my stack up, when I say, okay, I go select 1 ounce copper, but I always change the copper thickness to like 1 mil for my inner layers. And I just pick 2 ounce copper and even change its mil for my outer layer, because I say, well, that's 1 ounce, but I want my 1 ounce, my 1 ounce outer layer, I just make it like 2.1 mils and just say, well, yeah, it's 1 ounce base plus plating. I know what that thickness is going to be, and I just use that in my stack up and let the impedance calculator calculate based off of what the real number is going to be, not what the ideal number is going to be, or the nominal case is going to be. Does that answer your question there, Mattia?
Yeah, clear. So it is actually a quite, let's say, you cannot just design in a bubble.
No, never ever design in a bubble. Designing in a bubble is when bad things happen.
Okay, thank you.
All right, great questions. Any other? Let's see. And there's a question came in, but it was a direct. Is it possible to start out with a stack up provided by your fabricator, but then the fabricator requesting a slight tweak, 1 mil for 90 mil stack up on receiving Gerbers? When you say provided by the fabricator, do you mean you sent them your stack up and then they want to tweak it after they get the Gerber, or do you mean you ask them to give you a stack up that they approve, right? Basically I'm asking, are you asking them to completely give you a stack up, or are you asking them to review and approve your stack up?
The one where they give you a stack up, which they expect should be the stack up.
So if they've given you the stack up, they're basically agreeing to that up front. So usually if they do that, you're usually not getting hardly any tweaks. The only thing they might ask for is not necessarily in Z-axis, but would be in trace width, right? If they say gave you a stack up that had like 1 ounce copper in it, but you violated the minimum clearances here, which is the next topic we're going to talk about here real quick. It's not a slide. It should be. I will add it at some future date. So now the other thing that always happens with stack ups, and this is the other thing that you guys do need to understand. We've talked about this a little bit, but let me be clear about this. You build up a stack up that says, I want my board to be, say, 62 mils thick. There is always a tolerance on that, say plus or minus 10%, which is typical, because what the fabricator is going to see is in the same way based off of what the density of the copper on the layer is. So back when we're over here, all the way back up here before we got to lamination, right here, at this one here, right? If I have almost solid copper between these two layers right here, then, right, if it's like a plain layer, there's not as much room or volume here that resin needs to flow into, so this layer will be a little bit thicker. Whereas if it's very open, like say this layer right here, where there's almost no copper on this layer, there's a lot more volume that the resin needs to fill in, so that layer will be a little bit thinner. So yes, the actual thickness you will get back for your board will be within the 10% tolerance, but might not be the exact, like to the third decimal place thickness that you had worked out with your fabricator early on. Okay, so that's within the standard manufacturing tolerance. Okay, now the other thing to talk about over here, whoop, too far. Okay, is what we call the etch compensation. I mentioned it on a previous slide. One of the things that your fabricator is going to provide, and we've talked about this a little bit, is a minimum based off of the copper weight for the layer. The fabricator is going to define for you a absolute minimum feature width and spacing between features here. And this is because, as I mentioned, the fabricator is going to do what they call that compensation. And the way that compensation works is like as follows. We go into our board right here, our book. Okay, we'll go there. And I'll start with green right here. Okay. So now let's say I started with 1 ounce copper. Now I'm going to use 1 square here to represent 1 mil. There's my two features, right? Now, my fabricator, in order to do that etch compensation, it's about a 1-to-1. So let's assume that I'm doing 1 mil of feature size. That means my fabricator, in order to have my copper feature finish this size, and again, let me do a lighter orange right here, just to indicate the copper that's being removed right here. So my fabricator in the data is going to increase those two features by that 1 mil, so a mil on each side like that, so that after the etching process, right here, my feature can still be, I still have the gap between them I need, and so on. On the other hand, let's take a look at the same design right here. So that was in 1 ounce. Let's see what happens if I try to do the same thing, but in 2 ounce. Okay. And again, I'll use the light orange. Right here. Now in this one, because I've got 2 thicknesses of copper here, or 2 ounces of thickness, my fabricator has to increase 2 squares on each side. Now what ends up happening is this gap right here is so narrow that even if they could get those up, so there's a certain limitation because of how much the fabricator has to oversize, that they might get to the point where they get no gap here, right? Or too small of a gap for the etching to occur. So the fabricator is going to have a limit to how close I can put 2 of these features to each other, and they're still able to fabricate that. And again, there'll be capabilities charts. It's worth a call to your fabricator to ask them, to say, hey, based off of, right, based off of the fact that I want to use 1 ounce copper or 2 ounce copper or whatever the case is, what is my minimum trace and minimum spacing? And they will actually tell you based off of their process what those limitations are. Okay, is everybody good with that? Understanding that the thicker the copper you have to etch through, the larger the feature has to be, and the larger the gap between features needs to be. Okay, excellent. Let's do the last couple of slides here, and then we'll take a quick break of this section here. Okay, so we have this electrically finished board. We still need to add surface finish, panel routing, and solder mask, but electrically it's a completed board. So solder mask, we're going to use an LPI. Historically, there were wet film and dry film that were applied similar to the etch resist in a sheet form, which is compression rollers, but you did not get good coverage. You usually have little air gaps and so on. So now we use a liquid type solder mask. We call it LPI, liquid photo imageable. We refer to the acronym SMOBC. Some people add a vowel sound in there, pronounce it SMOBIC, but whatever. SMOBC stands for solder mask over bare copper. It's used to protect the copper on the surface from oxidation. It's used to prevent solder bridging during the soldering process, and we will not use it where soldering needs to occur. We will image it and either UV or thermal cure. There's both methods exist, UV cure and thermal cure or IR image cure. We'll use a similar process that we did for the etch resist. We'll have a screen printer or a direct imager head that will go in. We'll apply it as a liquid. We will cure or harden it where we want to stick, and then we'll wash the excess off, and so on. I just realized something right there. I didn't like the fact that my word occur was on the next page. Okay, once we have cured the solder mask, we talked about that last week, we will then apply a surface finish. Hassel is still one of the most common. We talked about that last week, or Enig or Anypig. Immersion silver, immersion tin. There's multiples. We'll talk about several of those after break. Surface finish is going to be used to protect exposed copper from oxidation. And also a solderable surface. There are several types, with tin lead still being the most common, which is the hot air solder or hot air knife leveled, hot air solder leveled. Basically, you dip the board in a vat of molten solder. When you pull it out, use hot air blades, kind of like hot air fans, kind of like when you go through a car wash and the hot air is drying the moisture off the surface of your car, or the hand air dryers when you wash your hands in a public restroom. Either case, using hot air to blow the excess solder off, leaving a skin behind. Finally, we've got legend, typically traditionally applied by a silk screening process we talked about last week. It's typically epoxy ink based, but that 4781 we talked about actually describes multiple different types. And again, as we talked about last week, a preferred ratio of about 10:1 for good text readability, and so on. Okay, with that, perfect place to take a break. We'll come back, we'll look at the PCB process flow, then the PCB assembly flow, and go from there. As always, I'll stay online if anybody's got any questions, but otherwise, let's take like 12 minutes, be back at like the 10 minutes after the hour mark. And if everybody's got any questions, feel free to ask.
Hi, Chris. I had a question.
Yes, question?
Yes. So while formatting, copying the format of the rooms in Altium, I was getting this error at times, called sequence error or channel offset error. Where, so what is this error, and how do we get this fixed?
Sure. Do you have your Altium open?
Yes.
Cool. Why don't you go ahead, share your screen, and I'll walk you through it real quick.
Let me see if it occurs again.
Well, even if it's not occurring, share your screen, and I'll show you where to look the next time that happens. Just because I already closed my Altium down, I don't want us to wait, the whole break for my Altium to restart and open up and everything.
Yep.
Okay, so first off, did it occur again?
I haven't looked at it in a while, but
Okay.
the other day I was seeing it.
Okay. Well, if you don't mind, can I take control of your system for a moment?
Yeah, no worries.
Did you click the? Okay, there we go. Oh, cool. I like your little pink. Sorry, I'm just moving your Altium for a second because the menu was under my Zoom controls on my screen, so that you guys don't see. Okay, so up here under the design menu,
Mhm.
under classes right here, not net classes, but component classes, right?
Yep.
And then we also have over here the channel classes right here. So for Hall effect, or let's take the LED, that's an easy one, right?
Mhm.
We should have LEDs 1 through 16 as the channel members, right? U LED 1 through U LED 16. Those are the names of the rooms. Sometimes, occasionally, this gets messed up and one of these gets removed or pulled out. Don't know why that happens. Or over here under the component classes, for example, ULED1 should have DS31 and R13-1. LED2, same two members, but now index 2, and so on. So you can check those two places to make sure all of the features are in there correctly. And then if they are not, usually the easiest ways to fix that is simply to do a update the PCB. Like go back into the schematic. Basically, this is where it's going to resynchronize everything between the schematic and the PCB document. So if that happens, 99% of the time, just go over here to the design menu and update the PCB document right here, and it'll fix, it'll regenerate all those room classes. But the other thing, like I said, that does happen occasionally. If that happens again, you just go over here and, like I said, under the design menu of the PC board, under the classes, A is under the channel classes right here. Make sure that all of the member channels are added correctly right here, that they didn't somehow get removed or some other thing like that. And also under the component classes, make sure that all the member classes have the same member items right here. So if the LED, for example, is DS3 and R13, make sure 1, 1, 2, 2, etc. Make sure you don't somehow all of a sudden, like, hey, why is there a, why did R13 8 get put in channel 7 or something like that, weird like that. So that's the two places to look for that when you get that channel offset error.
Gotcha. Thanks.
Okay. Hope that helps.
One another question.
Sure.
So say during the setting the rules, design rules, we are setting, for example, for 10 amp net class, the width is supposed to be so and so. So during routing, LTM automatically picks up that preferred width, or how does that work?
So you have the ability to set that. Go ahead, share your screen again, and I'll show you this here. And let me take control again. Okay, so first off, over here near little gear icon, which, by the way, I gotta say, love the pink arrow. Good call on the pink arrow. Very nice. But let's go up here to the gear icon. Oh, did that pull off on a different screen somewhere?
Yes.
Yeah, if you could drag that onto the screen. Okay. So up here, under the interactive routing, you're already in the right spot, PCB editor, interactive routing. track width mode, you can leave it as rule preferred as your default condition you're in. Same thing with the via size, right? The preferred, right? But there's also this checkbox right here that says pick up track width from existing routes. Okay. So if I do that, so let me hit the apply there. Let me just zoom in on one. Let's take this one right here, T15V. Okay. If I go up here to this one, and let me start like I'm on my top layer. Whoop. Okay. See, it's not even letting me route because P15V is in that 5 amp or 10 amp class. It's like, oh, I can't put a trace that big. So I can hit my tab, pull up my properties and say, yeah, 560, that's too big. I'm going to go to say 100 mils coming out of here. Whoa. Oh, you've got the dreaded auto pan turned on. Oh, that's so evil. I don't like the auto pan. Right? So I can pick this up right here. Okay. So now if I go back to start routing again, because I have that checkbox turned on, even though I've got my rule set up to be width as, right, or better yet, let me get out of that. Let me go back in here. Tab. So let me set up preferred again. Or better yet. Let me set it up at preferred. Doesn't matter if it's too big or too small. Okay. I'm going to come over here. Because I left the track at 100 mils, regardless of what I did in my rule, it's going to pick it up at the same width that it was at. You see what you see what I'm doing?
Yeah.
Right here. Versus if I go back into the gear and turn off the pickup track ends, and go back over here. No, I should have back here again. Go back to the preferred. Now it's trying to pick up my preferred width, even though I left a track at the other width. Right there.
Yeah.
Okay. So it's all about how you've got those configuration gear turned on.
Okay.
So I always pick up from rule ends. I leave these as preferred, but I pick up from track ends. Because in all honesty, like I said, this width right here is only if I'm actually trying to route this, but we have a plane for 15 volts or 5 volts or whatever it is. So I don't actually need, you know, I don't actually need to route this because I have that much width as trace it, you know, as a plane internally.
Right.
Now, I will ask you one other question. Since I saw your setting here, do you like the auto pan or would you rather have that turned off?
I do like it actually.
Okay, cool.
Yeah.
If you like it, that's fine. Me, I detest
do.
auto pan. I turn it off. But since we have it open, just for the rest of the class, since we're recording this, if you wish to turn the auto pan off, that's up here under your configuration or preferences gear icon right here. Under the general tab, enable auto pan. And for the schematic, it's under the graphical editing tab, enable auto pan. So if you don't like it, feel free to turn it off. I do all the time. But yes, Niti, as far as yours go, yes, the track width, it will pick that up based off of the gear icon and whether or not you set up as preferred. honestly, those big fat traces, we put those in there just so that there would be the ability to go wider if you needed to in certain areas. But for the most part, we're going to come out, drop a via, and go right into our layers. Or right into our planes, I mean.
Thank you.
Right. Great question, though. Okay, excellent. Let me go back over here. Let me go back and share my screen again. All right, so everybody back from break? I hope. Yes. Alrighty then. Okay, let's go through here. So this is an example. I will zoom in on this so you guys can go back and freeze frame this. I've spent time on this slide before, but honestly, it's just there. IPC put this together as kind of like a cartoon picture. The couple of key things to point out here are these yellow rooms. Because we're doing a photolithography process, but we're doing it not with standard photography that needs red light to protect, but because we're doing UV photolithography to process those diazo or silver emulsion films that we talked about, we actually use yellow as our filter color so we don't inadvertently expose our mylar films and so on. And then there's front end technical department here. So, and all fabricators as well as assemblers typically have on-site laboratory, chemistry / inspection and quality departments as well, and so on. So we'll look through several of these process steps here going forward here. But I just want to point out a couple of things. So zoomed in on that so you guys could freeze frame it if you want to take a closer look at it. You can also find it on IPC's webpage and go from there. Now, the PCB process flow. So we've already talked about all these steps except for one. So issue material, of course, that's just, where they go into a stock room and get the different sheets of pre-preg and cores and stuff that you're going to use. The resist coat, the UV expose, the develop, etch, and strip. This is the step we have not talked about yet, oxide. AOI, automated optical inspection, lamination, drilling, electroless copper, resist coat, UV expose, develop, more inspection steps, pattern plating with copper and tin that we talked about, strip the resist, strip the tin, pre-mask and more inspections, solder mask, surface finish, inspection, silkscreen, NC route. This is removing the board from the panel, final electrical test, final inspection, and ship. Okay, so first off, the photoresist. So traditional photoresist was applied as a film to the core or the board stack. Again, it's on these big rollers. There's basically like a sticky tackiness to it. And there's compression rollers right here that basically compression roll it onto your board surface right here, either single sided like you see here or double sided like you see right here. Either case, so this is an image of the double sided one. It'll be cured or hardened to the board surface where we wish, where we want it to, either where we want to keep copper or remove copper, depending on which step. There is development in a liquid photo imageable resist coat that's being applied now, so they can get some thinner layers for like the thinner and thinner coppers. Again, used to protect copper from etching in the acid solution. Develop, etch, strip. It's a one big long machine. This end of the machine is connected to that yellow room, and the film with the board, the core and everything is fed right in here. It's a completely closed system. Goes through developing onto the resin. The film is pulled off. The stripping of the etch resist, the acid stripping of the copper, stripping of the cured etch resist, and so on, all the way out here. So it's one big long machine that does all the various different steps for us. The core board or coated with the photoresist is loaded into the machine along with the copper pattern data. This type of machine uses silver emulsion on mylar film. Image is cured, usually under UV light. The remaining photoresist is removed. The core or board is then copper etched, and the remaining photoresist is stripped off of the core or the board. This is the new step, oxide treatment. Oxides are applied to copper surfaces to, quote, roughen the surface to promote resin adhesion. I may have asked this already. So many classes, hard to keep up with all of them. Who out there can explain or tell me how does a adhesive resin actually bond two surfaces together? And when I say adhesive resin, I'm using it as a general term for any adhesive glue. Could be super glue, could be epoxy, urethane, Elmer's white glue, wood glue, does not matter. Any adhesive based resin. Can anybody out there explain to me how that actually bonds two surfaces together? Yes? No? Ah, I see. Ah, if I put something down in the chat. Yes, the troughs and peaks, or peaks and valleys, nooks, cracks and crags, nooks and crannies, or whatever your favorite, metaphor euphemism is. But basically, the idea is that although we can take a machined metal surface like aluminum or steel or something like that, machine it and polish it smooth, that's only at the surface. When we look at it microscopically, there will always be some amount of surface roughness like this. And so the adhesive resins in their liquid state flow into these cracks, crags, nooks, crannies, peaks and troughs, whatever you want to call them. And anytime there's an overhang like this, once the resin gets in there and then hardens, it now has a mechanical interference that the hardened resin is a solid is now pulling against. And so you basically have a mechanical interference. Now, one little micro trough like this isn't going to do much. A billion or a trillion or however many you have in here on the surface roughness of a material like that is more than enough to handle whatever adhesive bonding strength we have. In order to promote that bonding in traditional board fabrication, an oxide is applied to the surface of the copper after the etching. So the exposed surface, not the surface that's already bonded to the laminate, but the exposed surfaces right here are treated with an oxide that intentionally roughens up the surfaces so that you can get these kind of cross-section of these nooks and cracks and crannies. There are three basic types that are used: brown, black, and white. Brown is very common. The black and the white are less so. I believe the black is more aggressive and the white is less so. It's a question to ask your fabricator what the chemistry difference is between those. But I know brown is one of the most common ones used nowadays. And you can kind of see it right here, the browning of that surface. That is the application of the oxide, which then gives the surface roughness here. However, this is becoming a problem in that newer boards with very, very thin dielectrics, such as the low profile, ultra low profile, no profile, or get to put VLP in here. So there's three types. There's low profile, very low profile, and ultra low profile, so that's no profile coppers. These are used quite heavily in RF boards, where the copper is so thin that any amount of surface roughness would degrade the performance of the RF features to the point where it would no longer act properly as a trace for the RF features. So as we get into these lower and lower profile, thinner and thinner coppers, the ability to add this roughness becomes a problem. And just an example. So our 1 mil, right, or our 50 micron that we just saw, 2 mil thick, right? 1 or 2 microns of surface roughness in a copper thickness that is on the order of, 35, 50 microns of thickness is negligible. It's not going to hurt us. 1 or 2 microns of copper roughness on a copper that's only 2 or 5 microns thick to begin with, like 1 micron in a 2 micron thick copper that we'll see sometimes in RF, that's 50% of my copper thickness gone. So in RF, we do other techniques in order to get good surface bonding without having to roughen the copper surface, but that's for my RF course, and so on. Automated optical inspection. Again, this uses camera technology here. Yes. Question. Kevin had a question out there.
Yeah, I was just wondering for the for that case where you are doing a layout on an RF board where this is important, is this generally like a note that happens on the fab to have them so that the surface roughness is within, you know, what you need it?
So it's not a surface roughness note. Typically, like in RF boards, what we'll do is especially in the RF sections, we'll say no oxide treatment to the traces in this area, or no oxide treatment. And typically, the fabricators do that as a matter of course. As soon as you start specifying, so there's actual IPC specifications for those three types there: low profile, very low profile, and ultra low or no profile copper. They have specific definitions of what their thicknesses need to be. So we typically say no surface roughness allowed on the copper. And what the fabricators will do is instead they'll do a chemical treatment to the exposed epoxy or resin surrounding it and allow the bonding only to the other resin and not to the copper, or whatever you get without roughening the copper surface to get extra bonding. But
Thanks.
But yeah, you typically very rarely, and let me qualify it this way. The standard surface roughness note that you see, that one that looks like the square root symbol, that is for mechanical engineering telling a machine shop how to mill and polish a metal surface, right? We don't do that in boards. It's copper, right? There's no milling, machining, and polishing going on. We're simply etching. Right? So we typically don't do a surface finish or surface roughness finish requirement. Instead, we put a note that says whatever the copper was, we ordered it. By the definition, if we ordered it, it had to come in from the laminate supplier already with this surface finish. So just don't roughen it. Leave it as is.
So basically, the most important thing is just specifying the correct finish.
The copper profile, yeah.
Yeah, copper profile, correct.
Yeah, because the standard coppers we use, the EDs and so on, don't have a required roughness or surface finish or thickness or anything of that nature, right? It's all just, it is what it is, right? Whereas the newer profiles, low, very low, and ultra low, have prescribed roughnesses, finishes, and so on that have to come in from the supplier. So there's nothing to tell the fabricator that they have to go further machine and polish and that surface. It's already done.
So I guess I don't want to take too much more time, but just as digital signals start to get, you know, higher and higher in frequency, I mean, at what point do you think that the digital signals would require this?
That is a great question. It's really, you have to look at the fundamental frequency at that. And it's the same thing with the RF. We typically say in that like 2 to 5 gigahertz is roughly the cutoff frequency where we start saying, okay, that's where I need to start having these RF behaviors. And it gets into what we call skin effect, if you're familiar with that from electrical engineering, whereas you higher and higher and higher in frequency, almost all the energy is traveling on the outer surface or skin of the conductor and none in the core. As we typically say, that 2 to 5 gigahertz is about the cutoff frequency. So if you start running actual like 2 gigahertz or higher fundamental square wave content in your digital signals, yeah, you probably have to start looking at these kind of effects. Now, here's the thing though with digital. Even at those kind of frequencies, by the very nature of it being digital, it is very tolerant of noise, of glitches, of, you know, logic 1, and I'm going to use old TTL voltage levels, even though nobody does old school TTL anymore. Old school TTL, a logic 0 was anywhere from 0 volts to 0.8 volts, right? And a logic level 1 was anywhere from 2 volts to 5 volts. So even if I start seeing signal degradation because of the skin effect losses, I still have noise tolerance, where with true RF, it's single frequency sinusoid, where any degradation of that sinusoidal shape is degradation of my signal. With digital, even if I have degradation because of these effects, the skin effects and so on, by the very nature of it being a digital signal, it's more tolerant of signal degradation. Does that make sense?
Yeah, great. Yeah, thank you so much.
Yeah, not a problem. Okay. All right, automated optical inspection, used to inspect for defects before proceeding to the next step. Could be shorts where you had under etching, as you see right here. Could be opens where you had over etching. Note that the machine only flags the error a human final judgment. So basically, these automated optical inspections, they're really great at quickly going through because it's basically, automated computer camera systems that can go through, inspect the entire board for these, and it will see something like this. It'll flag it, but none of the fab shops I've ever been at, anywhere that I know of, will take what the AOI says as law that says, yep, this is absolutely a reject. It still takes a human inspector to make the final decision on pass, fail, accept, reject, does it go for rework, repair, or just complete scrap, and so on. So AOI is really good, but we still have a human inspector that makes the final judgment call. Lamination, as we talked about. So we take our board itself, all the various different layers, the outer foils, the cores, the prepregs, and so on. We stack them together. Now, this graphic shows the z-axis, but it's not showing all like the tooling pins. So all these plates have like a whole sequence of tooling pins in them that aligns everything to itself, aligns layer to layer and so on, not only through our board layers, but all these metal plate layers as well. But effectively, what we're going to make is this big sandwich where we have all of our board layers here. We then have release film. Because we are dealing with an adhesive resin in the form of, the epoxy that's gluing our board layers together, well, we have the same issue here is I don't want any of that resin to squeeze out, get on this sheet of steel down here, and then glue my board to the steel, right? So we have these sheets of what we call release film, which are basically a Teflon type material that the resin won't stick to this, and this won't let any of the resin stick to the steel here. So we've got release sheets, we've got a steel plate, more release sheets, steel plate, more release sheets, and then finally our larger steel plates, which are our tooling and our heavier mass, and those are going to have all of our tooling pins. Pins will usually be on the bottom with pins sticking up. We slide these over them, and once we make this whole sandwich stack right here, this whole stack is put in one of these slots. So this is a fairly high volume lamination machine here, but they all work roughly the same way. Most of the shops here in the States, I see 5, maybe 10 slots. I think I counted this one up. I think it was like 25 slots. So this is a fairly high volume one. But basically the idea is one of these sandwich stacks right here for one panel will fit in this slot right here. This plumbing right here is circulating a heated oil, and we'll use a heated oil because both electrical and air-based systems, so convection systems and electric-based heating systems, there's too much variance in the heat. Just like your heater at home, right, will turn on, will warm your house up, and then once it warms up, it'll turn off, and it'll allow the temperature to drop a significant amount below your set point before it turns the heater back on, because the last thing you want to do is have your heater turning on, off, around your around whatever your set point is. So there's always some hysteresis in there. So because of that cyclical nature, you don't get good uniform heating. And so instead, we're going to use a heated oil or other heated fluid that once we get to that temperature, because of the long duration of the high thermal capacity and long duration of change, once we get to a temperature, it will be able to get those plates exactly to that temperature and hold it at that temperature for a good long amount of time, sufficient amount to bring the resin here up to past the T sub G, where it'll turn into the resin state again, the liquid state. Once we get to that state, the hydraulic presses down here will turn on, squeezing all the plates together. That is what will give us what we call the squeeze out, as well as the causing the resin to squeeze around all the surfaces. And then the stack, once we get to that point, the stack is cooled down while it's still under pressure to help mitigate any warpage. There is one other thing I wanted to show you on this, which I don't have in a slide, but is a picture I have that I finally found again. I was wondering where I'd put it. And it's this one right here. So I was talking about that last week. I was talking about that the fabricators have methods to control how much resin comes out the edge of your panel. So looking at right here, looking at a fabrication panel. Here's a couple of different images of the fabrication panel right here. So number one, here you can start to see those little tooling holes around the edges of the panel, right? So this is a fabrication panel. Here's a couple of boards. Here's 3 copies of a board. You can see the photoresist on here. Now this has not gone through etching yet, so you can still see it's got all the copper on it. But number one, you can see the fabricator's coupons. So the fabricator will put these kind of test coupons all around the outside of the panel, and these are what allow the fabricator to make their tests and measurements. These are fabricated at the same time yours is, set up with the various test conditions, such as your minimum hole size, minimum pad size, trace geometries, and so on. So they can do all the tests they need to do without actually destroying one of your boards to make a measurement. But also what you're going to see here, so you've got this kind of a pattern here, the dots pattern right there, as well as this channel pattern that you see right here. So effectively, all of these copper is going to be removed. And so this one's actually got 1, 2, 3, 4, 5, 10, 15 copies of a board right here. We call these venting patterns right here because as the resin starts to liquefy and it's put under hydraulic pressure, so where you see the black right here or dark blue, that's where copper is going to remain. Basically, you're going to have this little channel right here. So rather than the resin just being able to completely squeeze out the edge, it must flow through the channel. And because of the back pressure from hydraulic force or fluid force, trying to squeeze out of a channel, just like if you have a narrowing of your garden hose at home, it increases pressure, and some of that pressure will push backwards, keeping more of the resin in the board area. So the fabricators actually do have techniques in their manufacturing panel, which will have no impact on your board at all, other than helping the fabricator to control how much of the resin of that layer from the prepreg sheets stays within the area of your board, and how much of it do they allow to squeeze out the edge of the panel, and so on. So I just wanted to show you guys that so you guys can get a feel for how the fabricators can, different techniques the fabricators have to control. Here they use dots, so the fluid has to flow around all these little dots over here. The dots are actually used for 2 purposes, both to control the venting flow, as well as they can be used for what's called copper thieving during the plating process. So this is an outer layer right here because you can see all the pads. So during the plating process, this helps keep a uniform copper thickness right here during the plating process, so you don't have overplating in like a low density area right here. So there's 2 purposes for keeping those there, and so on. But anyways, like I said, I just wanted to give you guys a quick look at that, just so you guys could see and understand that process right there. Warpage. I just talked about warpage. From IPC 2221, warpage is defined as bow and twist, with the value specified for the amount of bow and twist allowed is 0.75% of the distance for any boards that contain surface mount parts. And if your board is 100% through hole, the value specified is 1.5% of the distance. Bowing is twisting in one direction, or deformation in one direction or one axis. Twisting is deformation in 2 axes. So this is deformed in both X and Y. So we get a twist. A bow, in this case, we deformed only in Y, but not in X, so we got a bow. Okay. As we talked about previously, or especially in my course 1 or at the beginning of this, the difference in the Z-axis balancing. So wrong is where I have thicker copper on one side, thinner copper on the other side of that Z-axis midline. common having it, if I have it balanced, I won't get the bow and twist. And just an example of what it might look like coming out of the fabrication process right here. Okay. Bow and twist are usually caused by improper z-axis copper distribution. We've talked about that already. Warpage puts excess stress on starter joints and component bodies, and can also lead to improper mounting or alignment of boards to mounting hardware, because once I go through a bowing process like this, because of arc length and geometry we learned in school, if I go through a bowing or a twisting, the actual distance, if I measure this edge to this edge, is shorter than if it was in the completely flattened state, which means the mounting hole right here to another mounting hole on this side over here has now shortened by whatever that arc length distance is right there. And so if I'm relying on this to be lined up to, say, a standoff or other mounting hardware, I might not be able to get that to properly line up, and I'm now having to put mechanical stresses on my board. Okay, drilling process right here. Again, the board starts after it's been laminated. You can see the sheets of copper foil on the top surface right here. Automated drill machines will go and drill all the holes. The machines now are even automated to a point where they have the rack of drill tips right here, where they actually have built-in torque sensors as well as programming that basically can measure when the drill bit is starting to get dull, and it will simply automatically change out its drill bit so that all holes are drilled appropriately. Multiple panels can be drilled at the same time. Typically only drill the plated through holes, then come back after the solder mask process and so on to drill the non-plated through holes. However, it can lead to misregistration of non-plated through holes, so if that is critical, expect that certain non-plated holes, like tooling holes, should be drilled during the first or the primary drilling sequence. Additionally, so it's the ingress or egress points, basically the entry and exit points of a hole. Anybody who's ever drilled through like a piece of wood or even, thin metals like coppers or so, trying to do, work at home, do-it-yourself projects at home, knows that when the drill bit first starts cutting into the material and when it finally punches out the back end, it tends to have a little bit of a tear or a burr or a chip left in the material. That's fine if it's a piece of wood that I can sand down, for a stud that's going to repair some wall material. On the other hand, I don't want any burrs or tears or cuts in the copper of my surface. So often we'll use aluminum or other protection plates like this will be placed on the two surfaces here. So when I'm drilling through, I'm basically drilling through a sheet of material here that will act as basically a stopper plate, so any tearing, nicks, or burrs happens in this material and not in my copper material itself here. Okay. The plating processes. I've never gone back and changed this. This picture goes with this one. This picture goes with this one. I'm sorry, they're kitty corner. But we have the electroplating, first the electrolysis, then the electroplating. So with the electrolysis process here, we have the copper ion suspended in solution. It's a saturated or even supersaturated solution. If you remember your chemistry, that's because of at elevated temperatures. And if I hold it at an elevated temperature and then reduce the temperature, some of the dissolved molecules will settle out of solution and onto a surface. That's how we're getting the electroplating. There will also be a slight amount of movement or vibration here to cause the fluid to go back and forth between my holes, so I get a uniform plating process right here. And this is the kind of rack would be. The difference between this rack and this one here, you can see the electrical cabling right here to apply the charge to the boards for the electroplating process. This one's just submerged. So two different pictures. One of these days I'll get around to swapping these back around. In fact, why don't I just do it? I keep meaning to do it and I never do. There we go. Now they're right. Electroplating, electrolysis plating right here. Okay, so the first use of electrolysis, Uses heat and agitation to move solution through the drilled holes. Copper is placed on surface through dissolution from solution. Results in copper only a few microns thick, as we saw. Next is the electroplating process, where by having either a solution or a copper ingot attached to one of the electrodes, and our board surface being charged electrically with the opposite polarity, it will cause the copper to either settle out of solution or dissolve from a copper anode and go through solution and settle on the material over here. And that's how we'll get our copper plating process. This adds the main thickness of copper plating and uses an electrical current to deposit the copper onto the surface. External layer image processing. Repeat the process that we did for all the inner layers on the outer layers. We talked about that already. Mainly, I just wanted a picture here to show you what the board looks like, what the panel looks like after the tin plating, before the copper etching. So you can see we've gone all the way through, including adding the tin to the surface. You can see the blue photoresist. This is where we're going to strip copper, so we can see board surfaces here, 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 etc. You can again see some of the test coupons on the edge right here. And the interesting note is, again, how the blue etch resist, you can see, kind of outlines this fat trace right here, indicating that this is going to be a fat copper trace, and those blue are where the gap is going to be between the traces. Okay, solder mask application, we saw this last time. With the thickness and the mask registration here, typically applied with a screen coater right here. This is one of the newer processes right here. For the liquid style, where the board will go through here. If any of you have ever seen any glazed like donuts or anything being made, they're running down a conveyor and there's just a literal wall of liquid just raining down on it, and the board, the item goes through and it gets coated with that material. The same thing happens here. So literally the liquid solder mask is coming down as a curtain right here. Your board goes through on a conveyor, gets completely coated, and then goes through the curing process, hardening the solder mask where we wish to keep it, and then the rest is washed off. We then have the exposed pads and vias. And again, with a traditional process like this, we do run into the issue of the misregistration. Final finish. So we talked about hassle. That's pretty easy. That's where we dip the board in molten solder, pull it off, blow it off with hot air. But as you can see, both in the profile picture here, or sectional view here, as well as in the photograph right here, hassle or hot air leveling gives a non-uniform surface finish right here. We get a thinness here, a thickness here, a thickness bump right here. Same thing right here. You can get non-uniform coating on the surface because you're just dipping it in a liquid and blowing the excess off, but there's no uniform control of that. Ooh, that was interesting. Wow, that was weird. Don't know what I did there. ENIG is the second most common. This is a multi-step process using multiple chemical baths with activators, neutralizers between each step. So here you can see a process right here. And what we do is we have copper applied first, then we have a nickel phosphorus layer, then we have a gold layer applied to the nickel phosphorus. Again, you can see it's a much more involved process with many, many different chemical baths. But what you end up with is a very, very coplanar surface. So if your design, for example, BGAs or any of the QFN, DFN, SON type of footprints or anything like that, any of those cases, you'll want the coplanar surface, or if you need it, go with something like an ENIG or one of the other processes here. Now, this says no black pad right here. Black pad, I don't even have a slide on it. It's a phenomenon that used to occur with ENIG and other gold-bearing processes. Because gold does not like to bond directly to copper, we use the nickel layer, but nickel does not like to process without the phosphorus added to it. So we actually add nickel phosphorus. Early on, there wasn't as tight of a control of the amount of phosphorus in the nickel phosphorus layer here. And because the gold layer is very, very thin, what you ended up with, the phosphorus had a dull, dark gray or black tinge, and it made the gold have this black appearance to it rather than the shiny gold appearance we're used to seeing here. So it was believed that this was a degradation in the performance of the gold and was believed to have been a problem. It turns out, A, it wasn't. It was purely aesthetic, but it was rectified regardless. They did the testing and evaluation, and they were able to determine exact maximum percentage of the phosphor and the nickel phosphorus here to mitigate that. But yes, if you ever hear that, that's all black pad was. It turned out to be purely aesthetic and did not have a negative impact or degradation to the performance of the board itself. Okay. All right. Silkscreen or Legend ink. This is an example I'd mentioned last week of the newer inkjet printers here, where what you have, and they actually have machines like this now, they'll do both the solder mask as well as the Legend ink, two different print heads. Basically, you align the board up, and just like an inkjet printer where it starts feeding the page through and it prints a line at a time and prints your picture on there, it's doing the same thing now with both the solder mask as well as the Legend ink. And the nice thing with this, because it has the optical camera in the print head, rather than trying to rely on mechanical alignment of a piece of mylar film or whatever the case is to the actual surface of the board to try and get the opening lined up to the solder pad correctly, now you can simply program. Have the printer stop the solder mask printing. Maybe you want 3 mils or 2 mils, whatever your clearance is to the solder pad right here. So you simply stop the printer here, move the printer past, and restart printing the solder mask again. Same thing with the Legend ink. So you no longer rely on mechanical alignment. You are now relying on optical registration of the print head to the actual feature on the board for application of the solder masks and the Legend inks and so on. And again, they usually have, whether it's UV cure, IR for thermal cure, whatever the case is, they usually have the curing source directly in the printhead. So as soon as they're printing the material, they're actually curing it, or at least partially curing it, to the point where it can then be taken out, put in the oven if it's a thermal cure for the rest of the way, so you don't get the slump as well that we had talked about last week. So very nice new machines here that they have that do those kind of processes. Okay, the assembly process. We will we will get through as much of this as we can, and we'll have to come back and finish off the last couple of slides on Wednesday's class. Okay. So first, we'll start talking about the solder paste process here. Historically, solder paste was done with a stencil machine, and the stencils were like this. And let me zoom in on one. Originally, it was aluminum. Now I'm told that most shops have switched over to stainless steel. But in either case, it's the sheet of metal right here that is laser or chemically etched to have an opening for each individual solder pad. For example, right here, you can see like the resistors or capacitors. Each individual pad has an opening. I know you can't see it in this picture because I can't zoom in far enough. There's actually a opening for each individual pad, solder pad of this quad flat pack device right here, and so on. Anyways, so you will have the inkjet, you will have the solder paste machine. Let me get back right here. So applies the solder paste, usually screen stencil. Typically it was a thin aluminum, about 5 mils or so. Stainless steel is more common now with thicknesses of 1 to 2 mils possible. So as we go smaller and smaller feature sizes, think, 0402s, 0201s, 01005s, and so on, that as we get smaller and smaller, the thickness of our stencil needs to be thinner and thinner and thinner so that we could actually, to get the proper volume. Right, with volume is, right, area times height for a cube. Right? Well, if my stencil is so thick that to get the right volume, I'd have this microscopic laser pinhole that I couldn't squeeze any solder through, like we talked last week about that solder particle size. So in order to get the opening large enough to squeegee the solder paste through, we ended up having to go with thinner stencils, which meant getting away from aluminum and going to a stainless steel. Again, the solder paste we put on here, your board would come through on the conveyor over here, be raised up, aligned underneath, and then the squeegee would put the solder paste on right here, and the squeegee would come and literally squeegee it through, forcing it through the openings, and then it would come back and it would repeat the process over and over again. Newer machines, and we'll see a picture of it. Actually, I've got a picture of it over here in those pictures we were just looking at right here. Where's the one I'm looking for? Right here. Newer machines now are actually doing direct printing of the solder paste right on the pads, right from a dispenser with a dispenser nozzle on them, as opposed to basically the same picture right here, as opposed to having to have the stencil and mechanical alignment. Your board comes through underneath right here, and you literally have a dispensing tube that literally direct prints the solder paste directly on your board that way now. After solder paste is applied, next the components are done. The placement is performed by several different machines depending on the type of component. You can have the high-speed chip shooters like this one right here. This usually has multiple heads. And you order your parts, or your assembler orders your parts on what we call tape and reel. So this might be resistors or capacitors, whatever it is. The machine is programmed. It knows what slot the part is in. It'll come over. It'll pick the parts up off of the reels right here and go and quickly place them on the board where they need to be. Other machines here run a little bit slower, but they can handle larger reels of parts, things like ICs and connectors, BGAs, and so on. You could also load them off of trays or tubes or other type of parts like that. Once all of the boards, once all the parts get put on the board then has to go through the soldering process. Okay, we'll talk about the reflow soldering in a minute, but first we need to talk about selective soldering. As we do more and more and more surface mount, either 100% surface mount or vast majority surface mount boards with maybe only our connectors being through hole, we start talking about selective soldering. This is where if I have only a few through hole parts that I still want to go through a wave soldering process, I need to protect my surface mount parts that might be on the bottom side of the board so that they don't inadvertently get, well, we don't want them to inadvertently get hit with the liquid wave solder that could either A, bridge between them, or B, heat them up enough where they fall off into the solder bath. So one of the ways to do it is to use a thermally insulated material, polycarbonate or titanium if needs be, and make a pallet that your board sits into. It'll have little cavities hogged out. They'll protect the actual surface mount parts and only expose the through holes to the bottom side of the board. The other way of doing selective soldering now are machines like this one or this one here. And let me turn those off right there. Let me pick just that one and that one. This is what we call a selective wave solder pot. We call it a selective solder pot right here. Basically, you have a little micro fountain of solder that comes out of this center hole right here, and the pot surrounding it, or the opening surrounding it, catches any liquid that spills over from the assembly. And this thing will move, and we'll be able to do a wave solder to one pin at a time rather than having to have the whole board go through the wave. The other option you can do, there are companies that do a machine like this. This is actually kind of interesting. This does the equivalent of the old hand soldering, but now with a combination of lasers and soldering iron tip and a wire feeder right here. So this literally has the spool of solder wire like you would use in the lab, fed through the machine, and then uses a laser right here to heat the surface up, along with a little bit of we call it a little bit of hot air right here to help with that. And effectively what this is doing is it's heating up and soldering by hand soldering, wire soldering, but doing it one pin at a time again. So again, multiple different ways of getting your through hole pins soldered in a semi-automated process without having to go through wave solder, right? Then we have the reflow soldering. Reflow, this is going to be our most common method we're going to use to handle all of our surface mount parts. What we're going to have over here is we have this long oven. You can think of this like a big, huge industrial pizza oven. Boards come in through the conveyor on one end, and then each of these plates up here creates a temperature zone. And so we can create this entire temperature profile. So the first several zones will slowly ramp the board up in temperature to a preheat or soaking temperature. Then you'll have a number of zones in a row that'll hold the board at that temperature, however many are necessary, so that the board material as well as all the components on the board get up to a certain given temperature below the liquidus temperature, but sufficiently warm that it can get to that temperature pretty quickly. Once we know we've soaked, we'll then do another ramp up. And so here's our solidus, here's our liquidus, back to our solidus again. So there's our history we talked about. So we go past solidus to liquidus, we get it melted, and then we quickly come back past solidus so it solidifies. And then we do a controlled rate of cooling with the last several stages that aren't shown right here in order to get our board down to have a proper solder joint formation. So again, this is all. Now, under normal operation, these lids are closed. This is at the trade show. This is at Apex. So the vendor just had, you can see the Apex, uh, booth number on the floor right there. So they're just demonstrating their machine. It's not actually powered up. Although one of the vendors always brings their entire line and has the full thing powered up and running. And so on. And this is just a picture I had in there that just showed. Now this came from an Asian vendor, so they start on the right and exit on the left, but same idea, loader, printer, they call them mounters instead of pick and place machines, reflow, unload, and so on. I like to just add a couple of cool pictures here of what some of the different machine things might look like, and so on, and go from there. A note on final inspection here, and this is probably where we'll call it quits for today, and then we'll pick up on Wednesday with the last few slides right here. A note on inspection, both at the bare board level but more appropriately here at the component level. While we rely heavily on AOI and optical inspections and so on, parts can get passed that are defective that unless you do a proper functional test might be missed. And this is an example from my own career. This is circa late 2017, early 2018. I was in Michigan at a company. We had a batch of boards come in, and one of the boards was just marginal, like improper operation during its functional testing. We were, doing board bring up and functional testing. This happens to be a surface mount capacitor right here, and the part was mounted. You can see the flux residue on the bottom of the board, on the bottom of the part right here, and the part was mounted this way. So this is what it looked like from the top. And it was in a fairly dense area, so you couldn't get an optical inspection sideways to look at it sideways. And what happened was either doing pick and place or assembly or soldering, or somewhere along the way, this one cap got a mechanical shock, and a chunk of the cap broke out of it, the ceramic layers right here, to where it changed the behavior and the value of the capacitance of this part just enough that when this was put in the circuit did not operate as expected. Instead, it was improper. It was missed by AOI. So while we do want to rely on our AOI, we don't want it to be exclusive our only way of inspection. It's always incumbent on us as designers and companies to make sure we go through a proper inspection, test, bring up, functional test, and so on to make sure that nothing got missed like this. All right, with that, I will ask if there's any last questions on today's material. Otherwise, we will pick up on Wednesday, finish off the last 20 or so slides, and then get into this week's, continue working on our assignment. Yes, question, Kevin.
This was about the assignment, if this is a good time.
Sure.
Yeah. So if you've already covered this, you can point me to whatever lecture it is. But I was looking at the assignment notes, and it said assume class 3 plating for plated through hole.
Mhm.
And so I'm just wondering, like, how do I translate that? What should I be looking at? Or
That's
should I?
actually what we just looked at right here. The plating, we're going to assume the class 3 plating, which we're going to assume that, sorry, right here. The average plating for class 3 assumes that we're going to have 1 mil of plating thickness. So basically when you're trying to, so we already covered the how to size our vias. That was either week 1 or week 2's lecture, right? Where we had to determine what was, and you may have seen that already. Remember when we were doing did you see the video where we did the via size?
I might have been, I might have entered the class after that, but I can go back and
Yeah,
rewatch that.
it's either the week 1 or the week 2 lecture. So I've got in the video there, I show how to calculate the size of the via based off of the via cross section, right? Basically, the minimum size the via should be for a given trace to handle the same amount of current. The cross sections need to be the same. So you have to calculate the cross sectional area of your trace, and the cross sectional area of your via needs to be the same. Well, how do we calculate cross sectional area? Well, we take the OD of the via, and we're talking about the plated barrel. The OD of the via minus the ID of the hole, that gives us the thickness of the copper in the hole wall. And then doing some geometry, we can calculate what that wall thickness is. My assumption my statement there about assuming class 3 is assuming your wall thickness is the full 1 mil thick. If you assume class 1 or 2, your wall thickness is only 3/4 of a mil thick, or 0.8 instead of 1 mil thick. So you've got a thinner wall, which means you would need a larger diameter via to handle the same amount of current that you could handle with a class 3 via.
Okay, and then I guess the shape of microvia is not, we're not doing that for microvias. Is that true?
So for the microvias, we're not going to worry about the current handling here. I only want for this class. So I gave you the size of the microvias, but if you're actually interested in the microvias, come back and take my advanced design class where I go into much more detail about the design and construction of microvias, because microvias also have much thinner allowance of copper plating, which isn't covered in this class.
Okay.
There's a whole separate standard. Instead of the 2221 and 222, it's 2221 and 2226. Is the design standard for the sequential lamination HDI, which covers the microvias, that angled shape of the hole, the thinness of the copper, and so on. So outside the scope of this class to actually do the microvias. For this one, we're really only focusing the microvias on the design for the BGA area anyways.
Okay, and then last question: did you in your lecture when you talked about this sizing of the plating, did you display how we did that in Altium, or?
It's purely a mathematical calculation, and then Altium, we're just going to size it in the design rule and say, yeah, minimum hole size, minimum pad size, and so on.
Oh, okay.
But it's just a calculation, and yes, I went over how to do the calculation. And I believe in that calculation, I said, I'm going to assume 1 mil thickness for my copper plating. And for the rest of the class out there, now you see why now is where I'm tying back together to what we talked about in week 1 or 2, where I said, we're going to assume 1 mil thickness for the copper hole wall here. Now you see where I'm getting that from right here, because I'm assuming class 3, so 25 microns, or 0.984 microinches rounded up to 1,000 microinches, which is 1 mil.
Thank you.
Okay, yep. Great question, Kevin. Any other questions before we call it a day? All right. If there are no other questions, then in that case, let's call it a day here. I wish everybody a happy work week, and I will see everybody Wednesday morning.
Thank you.
Thank you. Bye.
Okay, bye, everybody.
Thank you.